Fellas, I'm gonna be honest. It's gonna be a dark day today. Unfortunately, the code is not the cleanest. It's not the shortest. Well, I tried to clean up as much as I could, but it's definitely not the fastest. It takes about 33 seconds to run, and that's with like the kind of necessary optimization you need to kind of solve it ish, or at least one of them. But yeah, but it's a graph problem, which is fun. So let's go ahead and start solving it. All right, so if you go ahead and see your input, we're going to turn into a grid because obviously that's what I love doing. We're going to use complex numbers because I'm like that. And so we'll go ahead and create, or we'll first parse our input. So we'll do for yr in enumerate, input dot split lines, for x value in enumerate row, and then we will do grid p xy, so the point xy is equal to whatever the value is. I'm storing everything this time. If our y is equal to 0 and our v is equal to this period, that means we have a start position. So we'll do start is equal to point xy. And then similarly, if we have a, this be the end, so it'll be len input.split lines. And then this is the end. So now we're basically parsing our grid, and then we're also saving our start and end points. And then from this, I'm going to go ahead and actually create a class, two classes. So I'm going to have a graph. I'm going to create a node. So let's do our node first because it's actually fairly small. All we're going to save is self.pause equal to pause. And we're going to just initialize some like dummy kind of data. So it'll be edges, self.direction is equal to none. So this will basically store if it's a directed node, meaning it's one of these little arrows, and this will store its edges. All right, so now with our graph, what we'll do is def init, and we're going to take in a grid, start, and an end. And here, we'll leave it like this for now. Self.nodes is equal to an empty dictionary, and for p, v, and grid.items, if v is equal to a period, then self.nodes at our position, so basically our location value, is going to be equal to our node p. And then if v in slopes, and let's actually go ahead and define these first, these little constants, we'll do directions is equal to up, right, left, or up, right, down, left. And then slopes is going to be equal to, if I zip these up, so up, right, down, left, directions. So now I have a dictionary mapping these to its corresponding direction with complex numbers. And so now, why are you, you're not complaining, it's going to be this here. This will go away in a second there. All right, so now self.nodes p. So if it's a slope, we're going to make it a new node. And we will go ahead and self.nodes p. So this node will set its direction equal to the mapped value of slopes at our current value. So for example, if I see that I'm at a slope this, direction will map it to 1, which is meaning 1 to the right. And then I will store its direction as this. Otherwise, it'll be none. So now we have this. And then I'm going to put a line here, just a little spoiler. And then now, what we'll do is we'll override our original nodes. So start is equal to node start. So we're overriding the original node to define it like this, which now that I think about it, we really do not have to do because this is just a position in here. So instead, we'll just go ahead and do self.start is equal to self.nodes at start because we want to record these. All right, hopefully this doesn't break anything and I was just stupid when I was writing it the first time. But so now with this, we'll do for p and n in self.nodes, we'll actually build up the edges on the graph. So for each node, we'll say, hey, for each direction, if p plus d in self.nodes and self.nodes p plus d, edges n is equal to 1. Oh, let me write this down, I'll explain in a second. P plus d is 1. Alright, so what we're saying is for each node, for each direction from that node, if that direction exists in the graph. So for example, if I'm at this node, I check up, it's not in the graph. Like it's not one of my nodes. Then I look to the right, it is a node. Then we'll add that edge by adding it to our edges dictionary, and we'll set the value to 1, which is the distance. And this may seem crazy, but you'll see why we do this in a second. And then we also go to that node and add it backwards. So this way I'm basically adding all of these, and I'm realizing I don't need to do this. Okay, because we're doing this for every single node, this will end up duplicating it. So I could just only add it once. It's not really a problem. It'll just overwrite it anyway, but that should be good now. And then, now I'm thinking about it, I could optimize my code a little bit cleaner. So you know what? Let's kind of do that right here. So the problem here is this is adding every single edge. But for example, if I'm at this node, okay, let's say if I'm at this node, I should be able to add this edge and this edge. That's fine. But if I'm at this node, I should be able to add this edge. If I'm at this node, I should not be able to add this edge because it's a directed node. So what I'll do is if self.nodes p plus d dot directed or direction is, so if this is none, we're good. Or if this is equal to whatever our current direction is, or something like that, we should be good. Like for example, I'm at this node and I'm looking to the left. That is going the complete opposite direction of what this is, so I'm just going to toss on a negative. But what this is basically saying is, hey, look at the node. I'm looking at each of my neighbors. I'll look at this neighbor. Hey, is this one in the graph? First of all, yes. Second of all, is it either an undirected node or is it going completely opposite to the way I'm facing? If it is, I shouldn't have the edge, so I should have D. All right, so this is basically saying, hey, either like only add the node if, and this should be the other way around. So I want to add the other node. But this is saying, hey, only add that node if it's an undirected node or I'm going in that direction. So now, hopefully with that, let's go ahead and write our solving function. Def solve self. And so what this should do is basically start at the beginning, go and then keep doing like some kind of search. So we'll do depth first search and try to find all the paths to this end node and say how long they take. So we'll do answer is equal to 0 and then we'll return answer at the end. Then we're going to create a stack. And the reason I'm using a stack here, and it's still a list, I'm like, who am I kidding? But we're basically going to be popping from the end and adding to the end. This makes it a depth first search, and if you like look into it a little bit, it's better for like time complexity. It's not the same, it's the same time complexity, but it's less space, and so that's good. And so in this, each of our kind of values will be our node, our distance, and the set or like the list of things that we have seen. And now what we'll do is while we have our stack and dist seen is equal to s.pop, and we pop from the end, we'll do if n is equal to self.end. So if we are at the end node, answer will be the max of answer and dist. So basically store the best value we've seen. And then we'll do for e in edges, if e not in seen. So we look at all of the edges on our node, and if we haven't already visited that node in our current path, then let's go ahead and add this to the list of things, the stack of things we should be exploring. And I'll explain this in a second. I believe this should work. If not, I will come back to this line. All right. But so I think this should be fine. But what we're doing here is basically for each edge from our node, if we have not already visited that node in this current state, then add that to the stack of things we want to explore by adding that node. The distance is going to be how far it takes us to get to that node, which in our case currently is only 1, but we will change that. And then here, we're basically just adding it to a list of seen. All right, and then now we'll finally return our answer, and then I believe we should be good to create our graph and try solving it. So return, and I can actually just go ahead and call this all in one line. So graph, we'll take in a grid, start, end, and I'll call solve on it. I'll return nothing else, just to like follow my little program. If I run on the test case, let's see what errors we get. Cool. Alright, grid is not defined. Grid is not defined because maybe I didn't define it. Alright. End is not defined. Alright, end is, oh, this is supposed to be len of this minus 1 because the length will give us like one value past the highest index we'll see. So now we get 94. Perfect. And that's the test case answer. And if I go ahead and I run this on my solution, it'll take a little bit and then it'll crank out the correct answer, I'm hoping. Yep, perfect. All right, cool. So what time are we at? 10 minutes. All right, so now for part 2, all it is it basically makes the question simpler. Slopes mean nothing anymore. So all we have to do for our code will be part 1. And here, we'll only do if part 1. If it is a slope, we'll say it's directed. Otherwise, we just ignore it and we treat it like a normal point. That's it. And so now our code is done. Except, actually, I'll just to kind of tease you guys a little bit. Cool. That's lovely. Oh, that would do it. So this is true for part 1, and then we'll go ahead and now do this for part 2. Cool. Wow, we got the right answer. Look how fast that ran. What happens if I just submit my code? I'm not even going to submit it because, spoiler, you're going to be sitting here for a couple hours because for some reason this graph becomes monstrously huge. So what we have to do is some kind of optimization. And finding the largest path is actually like an NP hard question, meaning it is computationally really difficult. So we just kind of have to optimize our code. And so what a lot of people did was just compress your graph. So first of all, I'll create a function and I'll explain kind of the logic behind this. So when I have this graph like this, is there any other way for me to get from this node to, let's say, this node? And the answer would be no. It's always going to take you the exact same amount of steps because the only path I could go is here. So instead of having one edge like this, 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 all the way, I can just compress all of these into one edge that has a length of however much it takes. So to do that, it's actually fairly straightforward. All I have to do is look at my other monitor and copy the code, which will be deleted. Or, we don't even need this. All right, cool. I really did not clean up my code that much. All right. So what we'll do is for n insult the nodes.values. So this is basically where nodes is giving us, the key is the position, the value is the actual node object. We're just going to touch the objects. And then what we're going to do is here. If n is not none, so if it's a directed node, I'm just not going to touch it because I don't want to mess with it and it scares me. Then we'll do if len n.edges is equal to 2. So if you look at like any of these corridor things, that means basically I can only go in a straight line. Even on these bends, I can only go along one path or I could go backwards, which is the kind of nodes we can erase. So if this is the case, and just to, because I'm afraid of breaking something and I don't want to worry about the logic, for e and so what this is basically saying is, hey, if you have exactly 2 edges and none of your edges are directed, meaning if I'm in a situation like this, I just can't be bothered to deal with logic issues. I'm just not going to compress this node because it's touching a directed one. And that's fine. Screw it. So, but if this condition is true, meaning I have 2 edges and neither of them are directed, I can just compress this. And so to do that, what I'm going to do is I'll do n1, n2 is equal to n.edges, .keys, and then I'll delete the edges. So I'll delete them from both of the lists. So I'm deleting, for example, if I'm compressing this node. I go to this node and I remove the edge to this. Then I go to this node and I remove the edge to this, so forth. And then now we have to add to both of them the new edges. So n1.edges, we'll add it to n2, and the distance is going to be sum n.edges.values. So basically, this however much it takes me to get to n1 for my n and n2 for my n, I can just add those together, and that's my new distance. And now I'll do this also for the other one to be symmetric. And then that is, I believe, it. And then now we'll just go ahead and enter init, and we'll just call it compress. And now if I go ahead and run this, just so it kind of adds to the suspense, let's run on the test case. Cool, 154, and look at that, 4 milliseconds. Wow. All right, if I now test out my thing, and we wait for 30 seconds for my code to run, then we hopefully should get the right answer. So in the meantime, I don't know what to fill this with, so I guess Python note on why I was worried about this. Originally in my code, I just had this because while I was debugging, I wanted to make sure this wasn't copying over the scene object. But that should be fine. Let me make sure I didn't mess up anything else. I think perfect, I did not. And the code works after 31 seconds. But hopefully this is like a fairly intuitive code that you can follow along with. Let me know if you have any questions, and happy solving.